Hi, good evening. Let us wait for some 5 minutes such that
Yeah,
people
I
are
think we can wait for
yeah.
few minutes now so that the others they can join.
Yes. Okay. I think we can start.
Yeah.
And
Okay, fine.
okay. How's the course going on? How the interference is going on? Good. Yeah, for you people, yeah, interference may have over, but yeah, we'll discuss how that
Yes.
problems can be solved. And also, yeah, if you want, I can show like that simulation part in MATLAB.
Yes, sir.
Okay. So we will start with our assignment part. And if you have any doubt, just unmute and ask. Okay, I'm going to share my screen. Just give me a moment. I'll have a call. Hello. Ah, yes, sir. Ah, yes, yes. ആ അതെ 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 ആ അതെ അതെ ആ അതെ അതെ ആ ആ ആ അതെ ആ ഒരു മിനിറ്റ് മോഡൽ ഞാൻ പറഞ്ഞുതരാം. X4R Pro MD, Sorval X4R Pro MD. ആ അതെ അതെ ആ 1000 ml ഉള്ളത്. ആ അതെ അതെ. പക്ഷെ നമ്മൾ 1000 ml ഒന്നും ഇട്ടില്ല. പക്ഷെ ജസ്റ്റ് മറ്റേ പ്രീ കൂളിംഗ് പോകുന്ന സമയത്ത് തന്നെ ആക്ച്വലി അത് മറ്റേ ഇന്റേണൽ എറർ 0.036 കാണിച്ചു. ആ ആ എന്ത് കേസ് ആയിട്ട് ജനറേറ്റ് ആയിട്ടുണ്ടല്ലോ. ഞാൻ ഇന്നലെ മെയിൽ അയച്ചിട്ടുണ്ട്. ആ അതെ, ഇന്ന് രാവിലെ. ആ അതെ. എന്നിട്ട് എന്നെ ഒരു ആ ആ ആ പിന്നെ ഇന്ന് രാവിലെ എന്നെ ഒരാൾ വിളിക്കുകയും ചെയ്തു. ഒന്നാമത്തെ പേര് ഒരു minute. ഞാൻ പറഞ്ഞുതരാം, പേര് പറഞ്ഞുതരാം. റോബിൻ അല്ല. വിഘ്നേഷ്. ആ അതെ, ഇന്ന് രാവിലെ വിളിച്ചു. അവര് തേഴ്സ്ഡേ ഓർ ഫ്രൈഡേ പറ്റിയാൽ വരാ, ഇല്ലെങ്കിൽ അതിന് മുന്നേ ആണെങ്കിൽ അവർ നോക്കിയിട്ട് എന്തെങ്കിലും മറ്റേ ഓൺലൈൻ വഴിയോ അല്ലെങ്കിൽ ഫോൺ വഴിയോ ചെയ്യാൻ പറ്റുന്നതാണെങ്കിൽ അവർ ചെയ്യാൻ ശ്രമിക്കാന്ന് പറഞ്ഞു. അല്ലെങ്കിൽ തേഴ്സ്ഡേ ഓർ ഫ്രൈഡേ ഡയറക്റ്റ് ആയിട്ട് വരുന്നു പറഞ്ഞു. ആ ആ ആ ആ ആ ആ ശരി. ഓക്കെ. Can you see my screen? Hello. Oh, can you people see my screen?
Yeah, sure.
Okay.
We're able to see it.
Yeah, sure. So we can start with our
Yes.
experiment.
Okay.
So the first question is like that way. The microscope
Yes.
interferometer is illuminated with a monochromatic light. One of its mirror is moved 2.53 into 10 raised to minus 5 meter, and it is observed 92 fringe pairs, bright and dark, passed by in the process. Determine the wavelength of the incident beam. Okay. So first we have to know how the fringe pattern in Michelson interferometer is changing when the arm is moved. Okay, we already know the diagram of a Michelson interferometer. So you have a monochromatic source, most probably a laser source will have. Then the laser source will provide a monochromatic beam, and then we will have a beam splitter. So we will have a beam splitter here. in 45-degree angle. So from the, and we will have a arrangement of two mirrors at one arm. There will be a mirror M1, and the other arm there will be a mirror M2. What will happen? The beam will split into two parts. One will reflect, since it is 45-degree, it will reflect to 90-degree, and it will hit in the mirror M1. The other part will transmit and hit to mirror M2. This M1 and M2 are like perfect mirrors, so they will reflect this rays back towards this beam splitter. Towards this beam splitter. This one also reflect back towards this beam splitter. And again, what will happen? From this beam splitter, some portion will get transmitted, and transmitted will go here, and some portion will get reflected. So reflected thing go here, and these two beams are actually getting interfered. Actually, perpendicular to this one, here also will be two beams, because of the transmitted beam from this right side and this reflected beam from this top one. Here also will be there, but we will not consider this portion, so we don't need that one. So we'll only consider the portion which is coming at the bottom portion. So here we will keep our detector or something what we require, and here actually we will get the interference fringes. Okay, this portion you people understood, na? This is the working principle of a Michelson interferometer. Okay,
Yes, sir.
this is okay, na? Now you see how actually the interference is happening here. Light here traveling, let it be this L1. This length of this thing I am saying as L1, and this length I am saying as L2. So let the light hit here. From here actually the process starts. After hitting the first beam splitter, the light will travel L1 distance upside. So first beam I will see light will travel L1 distance, then it will come back again one more L1 distance. Then actually it is transmitting and coming outside. Okay, and what about this one? The beam which is transmitted, this is for this first beam, so it is actually trans to L1, and in this case actually this beam is traveling L2 plus L2. So L2, so the beam 2 is traveling L2 plus L2 is traveling to L2. Actually there will be some cases like there will be some phase change and other things in between happening. Usually what we will do, actually in order to compensate the phase change, actually we will keep some transmitter, some glass block kind of thing in between to compensate the phase change. So actually, yeah, you don't need to consider the phase change. Just think that this is like a ideal case. It is actually traveling at 2 L1 distance up and down and reaching at this mirror, and this is traveling 2 L2 distance up left and right and reaching at this mirror. So this is the total path length traveled by the beam 1, and 2L2 is the actual path length divided by beam L2. And if this beam will have some particular phase relationship, they will undergo interference. This is the fundamentals of this Michelson interferometer. Okay, now come to the question. Now actually this is aligned in a proper way, and you are getting some fringes. Now your mirror actually moved from this position to some extra position here. So let the M2 is moved from this position to some more this position. Okay, and then they see that 92 fringes passed. So what they will see, just see that if you are seeing it in some microscope imaging system or something, actually you will see a lot of fringes like this way. Like this way you will see fringes, and you will see there will be some crosshair of this microscope will be something like this way, it is be here. So if you moved this mirror, you can see that this fringe will move through this crosshair, and and you got that one 92 fringe pairs, means dark bright dark bright things are actually passed, 92 pairs of fringes passed when you moved for a distance of, sorry, when you moved a distance of 2.53 into 10 raised to minus 5 meter. So you got 92 fringe pairs corresponding to 2.53 into 10 raised to minus 5 meter. Okay, now you see, from here actually I want to get the wavelength of the light. Now just think that you have a particular wave, and you have another beam. If both will have the
Same wavelength.
same phase, you will get a constructive interference. Okay, similar kind of two beams having the same phase, you will get a constructive interference. Now if you want to get the exact same constructive interference, you have to move one wavelength upward. Okay. Now also you will get a same constructive interference, but the position of this, the position of this beam was here. Now it is actually moved a lambda distance. Then also you will get a constructive interference. So if the beams are moved in multiple of lambda, you will get a constructive interference. Okay. Now you see, but what happened in the case of a mirror? If the mirror is at this position where light is hitting here and coming back. Now think that if you move your mirror to some distance d, how much extra distance light is traveling?
2D.
Yeah, light will travel 2d distance. So this 2 actually you have to count. So if you moved the mirror d distance, the actual path length traveled by light will be 2d. And if that path length is actually multiple of lambda, you will get a constructive interference. So they told that fringe pairs is gone. So means you dark and white, one dark and one bright fringe is gone, means the full, just again you are going to get a dark. If you start with a dark, then white and dark, means one fringe pair is gone, means one white. If you are in dark, then next one is a bright, then exact next dark middle you are going to see. So if you are moving like a 92 fringe pair, means 92 wavelength you traveled, but your this 2d you have to calculate. So 2 into how much distance?
2.53 into 10 to
2.53 into 10 raised to minus 5 is corresponding to some, okay, there is not some, it's already there told, 92 lambda. Okay,
Right.
so we will get lambda as a 2 into 2.53 into 10 raised to minus 5 divided by 90. What will be the answer?
550 nanometer.
Okay, we will get as a yeah, you get a 550 nanometer. Okay,
Right.
it's clear.
Right. So clear.
Okay, so let us move to the next question. So this is the thing. Actually, yeah, you have to see what kind of interferometer you are using, and you have to understand the working thing of the interferometer. Here in the solution, you can see that actually, yeah, the distance d associated with m fringes is equal to d is equal to m lambda by 2. But yeah, why this is like d is equal to m lambda by 2? It is coming. It's actually 2d is equal to m lambda. That's why it is coming as a d is equal to m lambda by 2. Why it is coming 2d? The 2d is coming because of it is a Michelson interferometer meter in which a beam is exactly traveling twice corresponding to your movement of your mirror. That you have to count. There are another interferometers are there. Like it is not beam is not exactly coming back. Like Max Hender interferometers are there. So in that thing, if you move one arm away keeping the same angle or something, you cannot directly use this kind of solutions. That you have to see. But yeah, I think Max Sandra also it will come like that because there also one reflection sand. But yeah, no, Max Sandra will not come. Yeah, it will exactly come like Dion. Okay, so actually you have to understand how that particular interferometer is working, and actually we are only looking what is the optical path length. So actually we have to go your optical path length. Okay, here actually optical path length will come double of your movement of your mirror.
Right.
Okay,
Yes, sir. Clear, sir.
next, which among the following are amplitude splitting interferometer? There are actually mainly we can say that there are two kinds of interferometer. We already know the basics of interferometry. Actually, what you have to do, there are two coherent beams have to be interfere by themselves. And how we can make them interfere? You have to get a two coherent beams. And usually what we will do, we will take a beam and we will split the beam. And the splitting of the beam is actually depends on, and based on the splitting of the beam, actually we can classify our interferometer as two. One is amplitude splitting interferometer, another is a wavefront splitting interferometer. So in the case of a amplitude splitting interferometer, what they will do, there will be some element like a beam splitter. So if I am giving a beam of intensity, so amplitude is something like a intensity. So I, it will split into two beams, something like a I by 2, and it will transmit the remaining I by 2 here. This is a 50-50 beam splitter. So it will transmit 50 percentage of your intensity or amplitude as reflected thing and 50 percentage as transmitted thing. And some, if it is like a 60-30 interferometer, reflection and transmission, it will split like a, whatever the intensity is coming, 60 percentage will get reflected and 30% will transmitted. Okay, like that way you can do different kind of interferometer. But actually what it is get splitting, actually it is splitting the beam amplitude as per according to the the requirement, it is yeah, according to the specification of the splitter, actually it is splitting the beam amplitude. Actually here actually we want some extra features. Now you can see that the splitted beams are actually moving like a almost like a 90-degree. Now it is our task to put some mirror and some arrangement such that it will come again and interfere. Okay, so this kind of interferometers are called amplitude splitting. So it's actually split the intensity or the amplitude as per the specification. Then another type of interferometers are there. So what they will do, actually they will split the wavefront. Just think that there's a point source. It is coming like this way. There will be some two kind of thing. This will be much more familiar for everybody. This is like our, this is nothing but our Young's double slit experiment kind of thing. What will happen when this source reaches here? This single wavefront will make two wavelets. So you can see that this is like a, the amplitude will be less because of your source is taking only one portion of this one, but this two portion will be exactly same amplitude if your slits width are same. But actually what it is splitting the wavefront at two different position, and these two wavefronts will interfere and to form interference pattern. Now you have questions. What are the things are amplitude splitting interferometer? So this Max Hender interferometer, how it is looking like? Microsine interferometer we already know, correct? Na? We already know the structure of this microsine interferometer. You can see the main part is actually a beam splitter. From here actually it is splitting beam to two parts. One is going perpendicularly upward, one is going perpendicular to horizontal direction, such that it is while coming back it is getting interfered. So this is an amplitude splitting interferometer. Then I said that there's another interferometer which is called a Max Hender interferometer. I'll just draw the diagram of that one, and you can see the Max Hender interferometer will also have a monochromatic source. So in microsine interferometer, what is happening? We are using single beam splitter, and the light is coming back to the same thing and getting interfered. In the case of microsine interferometer, we will have a two beam splitter. Beam splitter one. The beam splitter one will split the beams into two perpendicular direction. One will get transmitted R1, then put a T1, and at that path actually what we will put? We will put a mirror one, and we will put a M. What will happen? This will reflect towards here. This will also reflect towards here. At this point actually we will put a another beam splitter, the opposite, or you can put like this. So here what happens? This thing will, this R1, one portion will get reflected and it will go up, and in T1 also one portion will get reflected and go this side, but one portion will go to transmit this side, and here R1 is also one portion will go to transmit this side, and whatever is transmitted, so I put a T2 R1 will interfere with the reflected portion of T1. I'll put R2 T1. These two beams will be get interfered, and here also Yeah, here the reflected portion R2, R1 will interfere with the T2, T1. So you will get a two interference pattern at two mutually perpendicular directions. Okay. Here also you can see that what is actually getting split. Your amplitude is getting split. So this also an amplitude splitting interferometer. It's a Mach Zehnder interferometer. Okay. Next. So next is a Rayleigh interferometer. How a Rayleigh interferometer works? That you can check the diagram of a Rayleigh interferometer. For a Rayleigh interferometer, you will be have a light source. Then usually they will have a lens. It's like a point source or something, and this lens actually make if you kept something like near the focal point of the lens, actually your lens will make this light go to parallel. Okay, so you can say that the wavefront is coming like this way and it will become a parallel beam. Okay, and this parallel beam actually using some means, some cells or something, actually we they split into two. And after some time we'll keep another lens and that another imaging system and other things. So, after coming here, this portion and this portion, usually it's like a two different cells and they will put two different gases with the two different refracting tests like N1, N2, and they will check how these waves are getting interfered. After passing through this parallel lines through the lens, actually what will happen? It will again focus. This portion will get focused, and this portion also will get focused. Focusing means actually it is going to a single point. So what will happen? This thing will get interfered. So you see what is actually split here, whether they split that amplitude or they split the wavefront. You can see that this is actually a single wavefront, which actually, if it is a, after putting a thing, you can say that it's like almost like a big plane wavefront. So in the plane wavefront, they're divided into two. So actually they splitted the wavefront. And again, they combined them together and form the interference. So it's like a wavefront splitting interferometer. So the Rayleigh interferometer is a wavefront splitting interferometer. Okay, next. Diode's mirror. Diode's mirror is also the working of a diode's mirror is like that. You will have a light source.
Sir, I could not understand this render interferometer.
Max handle. This one.
Yes, sir.
Okay. Now you see that there will be a beam splitter.
Yes, sir.
Okay, I can put it again. Microcenter interferometer, you understand? Na?
Yes, sir.
Yeah. So what happens in the microcenter interferometer? One light source. This actually coming here, then one portion is getting reflected and one portion is getting transmitted. Okay,
Yes, sir.
the reflected is going to M1 and coming back to the beam splitter itself.
Yes, sir.
Transmitted is going to M2 and from the mirror it is reflected back to the same beam splitter itself.
Yes, sir.
In the case of a Mach Zehnder interferometer, you will have a light source. From the light source you will put your light to a beam splitter.
We have two beam splitters in this case.
Yes, it will go to a beam splitter. We put this notation to show a beam splitter. So what will happen? One portion is getting reflected. Okay, one portion is getting transmitted.
Yes, sir.
In the case of microcentrophotometer, we kept the mirror like this way and this way.
Yes, sir.
But in the case of a max 100 interferometer, we will keep the mirror in 45 degree. Here also in 45 degree. Okay. So what will happen to this beam? This will go perpendicular to this way. And the reflected beam I will draw with a different color.
This is deviation of path, just.
Yeah, this is actually path deviation. So actually the beam is splitted here. Here
Yes,
actually
sir.
beam splitted. Now it's actually path is deviating.
Intensity is divided into two,
Ah, yes.
then it is splitted.
Yeah. So this one I am putting it as like color. So now actually your beam is splitted to two. Now
Yes,
actually
sir.
you have to combine together such that only it will get interfere.
Yes.
So to combine here actually you will use another beam splitter. So from the beam splitter, this is not only like just splitting. So how a beam splitter work, it will partially reflect and partially transmit.
Yes.
So your blue can reflect this side and also some portion of blue will transmit here. Okay.
Yes, sir.
Similar way, your green can some portion can transmit here and some portion can reflect.
Yes, sir.
So here actually these things are actually came from the same beam.
Yes, sir.
So this is the path that will be like L1. Then if it's like exact a square geometry, this one also will be L1.
Yes, sir.
And if this is like a L2, this is like L2.
Yes, sir.
So if it's like exact in a rectangular manner, the total path traveled by this beam will be L1 plus L2.
Yes, sir.
This is like L2 plus L1.
Yes, sir.
So that will get interfere at this position. So the outcoming rays will be interfered rays. Okay.
Yes, sir.
Yeah. So what's the principle? Actually, they are splitting the amplitude. So it's a
Yes.
amplitude splitting interferometer. So in the case of a dioids, sorry, this Rayleigh interferometer, actually they are splitting the wavefront spatially in two parts.
Sir, in relay we can understand its wavefront splitting,
Yeah,
but in Xander and as well as previous interferometer
yeah,
Michelson's,
yeah,
both are splitting the amplitude only, no?
yeah. So you can say that it's like a same wavefront. It is splitting to two. With a high intensity wavefront, it is actually splitting to two low intensity wavefront.
Yes, sir.
So it's only splitting the amplitude. It is not splitting the same wavefront into two different positions.
Sir,
So
then what is the basic difference? Like what is the use of Xander and what is the use of Michelson? Like how can we segregate that which one is used at which place?
yeah, now you can see actually. Now you see that you want to know that was they are saying now. Yeah, you just tell that which is actually used as Young's double slit experiment. What kind of splitting is this one?
Yes, sir.
What kind of splitting? It's amplitude splitting or
This one is the amplitude. This is a
no?
wavefront splitting.
Yeah, it is a wavefront splitting. Now, now you say for wavefront splitting, what kind of coherence you require? Spatial coherence or temporal coherence?
For wavefronts, we require spatial coherence.
Yes, actually, you are actually splitting two spatially separated position of a same wavefront. So,
Yes.
if your spatial coherence is very good, only your wavefront splitting interferometer will work.
Okay.
Now,
Yes.
now you understand what about this one? Like
Yes,
your
sir.
Max Hender and our microcell interferometer. What they are combining? Actually, they are looking like how much path it is traveled.
Yes, sir.
So it's like they are actually comparing the path length. Here
Yes, sir.
actually you can see that the path lengths are actually almost same. Actually,
Yes,
it
sir.
is only the difference is like that way. It is from the same wavefront, but it is passes through two different medium or something like that, two different paths. But the length
Yes,
is path length they traveled is, if they didn't put any medium in between, they are actually same.
yes, sir.
So in that case, actually you required very high temporal coherence. So you can
Yes, sir.
use, yeah. So based on your requirement, actually you can see what are the things you want to study, like what kind of source you want. Actually, you see this is actually, yeah. Now you can see that if these two cells are not there, here there is not at all any interferometer. These are just like a lens focusing and just make it as beam parallel and then it's a focusing. But that position actually we split into two mechanically or physically, and we are going to study some characteristics features of our, like some gas or something like that. We fill these two cells with the two gas. Then actually what is happening, then there is actually a small shift in path length because of that gas which we introduced. Unless we introduce any gas there is no path length difference.
Okay.
Okay.
But this, sir, I have understood for this one. But I cannot now also understand the difference of usage of Zender and Michelson. Like, where can we use them? Because in both the case, the beam got splitted
Huh.
amplitude wise,
Ah.
and the path was deviated.
Ah, yeah.
Uh,
Here also, you can see that this path. Actually, this is a simple interferometer thing. But what we will do, actually, we will put some cells here. Our
okay,
like object under test, we will put here. Object under test is not like a our lens. It is like a liquid or something.
okay,
So like that way, if you want to study about some flames or something, so how
okay,
this temperature is actually affecting some mechanical path, or this we will heat some gas. First we will put like a two chamber with the same gas here. Then we will take
okay,
a interferometric pattern here. So it will have some particular fringe pattern here, and we will next we will heat this portion. So this will be like a,
okay,
this may change. Maybe sometimes it may increase the size of this wavefront or decrease the size of the wavefront, and based on that heating pattern, this refractive index inside may change, and it will give different information
O-
regarding
o-
our properties.
okay, sir.
Yeah.
Now I can get it.
Yeah. And thing here actually you see this one, and I'll just plot one Lloyd's mirror also. In the case of Lloyd's mirror, you will have a mirror and you will have a screen here. And what you will have a, you will have a source. From the source, what will happen? Actually, light will come as wavefront. Let us see. And I am just plotting like this way. Light will reach as a straight line here also, and some reflected portion it will reach here like this way. It will actually what they will do. Actually, putting they are splitting the wavefront in two in this case, and making them to travel a little bit of path length. This is will be a shortest path and it will move a little bit more. But here you can see that this is actually same wavefront splitted in two, and they made it to travel with a slight path difference. Here the path difference is actually introduced by arranging something in between.
Refractive index.
Yeah, that's actually we externally put it there. Here actually by originally actually they are putting some path difference because of it is traveled more distance. Like that you will get interference here. Here also what is actually getting interfered? It's actually getting interfered by two portion of the same wavefront, but that wavefront is actually traveled some extra path. But one thing is here, you can see that these things are actually, but see, in the case of a Young's double slit experiment and this our Bird's mirror experiment, what is the thing? Actually, you have to get a very good spatially coherent thing. So to make it like a very good spatially coherent thing, your size of your light source will get very much decreased. Then your intensity of your beam is also will get reduced very less. But in the case of a Mach Center or a microsend interferometer, you can use a very high power laser source itself, and you can nicely split that amplitude into a two, like a 50-50 itself. Now you can see that making that kind of interferometers is like now much easier compared to this interferometers. So it's like it depends on our users, we will use these kind of thing. Your microsend interferometer you are seeing like this way, we are saying like this, no, like it is now. Actually you can incorporate all this interferometer inside a fiber. So what you will actually see, you will see there will be a fiber, there will be optical fiber where you are going to couple your laser with that portion, and you will be a beam splitter. Beam splitter you cannot understand whether it is a, it is like it will be look like something a small portion where you will put one fiber and outside two fiber will come. So this is the beam splitter which is actually splitting your beam inside, and this is a single fiber. Yeah, you will see like this way, and this portion will go as some fixed mirror, and the mirror actually you will not at all see. The mirror will be actually incorporated at the end of your fiber. You cannot even see that one, and this portion will go towards the portion where you want to test your, where you want to measure the interferometer pattern, and actually they will measure the small distance in between. And how this output will come, this output will come from this side. So you will see like something like this way, one small portion containing two fiber. Here you will couple a laser, and here you will be some photo detector, and this arm is actually fixed, and this is only this portion you will use. So making this one is actually, you'll think that it is a difficult thing, but yeah, to get this one is very easier. And you see it's like a loss is like a very less, there will not be any loss, because the most of the light which is coupled with this fiber will pass through this optical fiber, and actually the beam splitter will have a very good efficiency, and that will actually split, let it be like a half half. So this half portion is go here, half portion is almost come here. Like that way actually you can get a very good interference pattern. So this is like a, this Mach Center kind of interferometer, and your microsend interferometers are actually now it's like modified in a manner that you can incorporate in a very small space, and you don't worry about losses and other thing, and it has a very high usages, like a measurement of it. Now you already see that it's like a, how this lambda by 2 or lambda by 4 is the precision which we can measure the distance. So it's like a 5 if you are using some green laser light or something, like a 500 nanometer, or like you can measure around the like a 300 nanometer or 200 nanometer size variation actually you can measure using this interferometer thing. or we can say that only by interferometer thing we can measure that much precision, because without any screw gauge or calipers we cannot at all measure like that way. So interferometry is like a very high application in the case of distance measurement in nanoscale. Okay, so yeah, so the Rayleigh interferometer and Lloyd's mirror are wavefront splitting interferometers, and this Max Handler interferometer and Michelson interferometers are amplitude splitting interferometers. These things are clear now. You people are hearing now? I'm not seeing the screen.
Yes, yes,
Okay.
Yes.
very clear.
Now see, what would be observed if white light is used instead of a monochromatic light in an interference experiment? Yeah, this may be a direct question. Same fringe pattern as in the case of monochromatic light. White bright fringes at the center with the colored fringes either side. Now interference pattern will be observed, shifted bright and dark fringes. What you will see?
White light,
White bright fringes at the, and what about the other pattern?
when a white light is it is split into multicolors.
Yes. Yeah. So you know that there is a, along with the interference there is a diffraction thing else also happen there.
Hmm.
When it is actually you in an interference experiment. So and actually this all splitting of this color and actually this bending of your color or of your light is actually depends on its wavelength. Okay. So just think in case of a our normal mm, Young's double slit experiment. You will have a one beam is coming, and this one beam is actually split into two beam. Okay. Now you can see that actually in this portion, at the middle portion, actually these beams are getting constructively interfere, and that's why you are getting an interference pattern like this way. Okay. So middle portion will be always a maximum. Like that way you will get a fringe pattern. Okay. So and this distance here also some maxima is coming, that's why you are getting a maxima, and this portion also you are getting a maxima, this portion also you are getting maxima, this portion you are getting maxima, and what is actually corresponding to that distance, how it is bending, the bending is also depends on the size of your slit as well as a wavelength of the light. Let us see that if your light is composed of a different wavelength and your slit size is same, what will happen? Now I just say that okay, I have a slit and I have a red light and I have a violet light. Okay, which will bend more, which will bend less? In the case of a prism, you people know.
Yeah, when a white light is there.
Yeah, if I put a white light there, which is composed of red and violet, which will bend more?
Violet.
Violet will bend more, red will bend less, such that you will get a VGO in this direction. You will get a VGO. But in the case of a diffraction, what will happen? I can say that this violet will bend less. Okay, because the interaction with that size is actually matters, and red will bend more. Okay, like this way. The bending will be more for violet, and bending will be more for red. So what will happen here? Just think that you are using a interference experiment composed of two wavelengths. Now I put red, now I put violet. Okay. Violet will also produce similar kind of interference pattern. Middle will be maximum, but the bending of violet will be less compared with the bending of red. So what will happen? The next will be somewhere here. Next will be somewhere here. Okay. Here also something like that. So what you will see at the middle portion, always every beam will come and interfere proper. Okay. So middle portion always will be composed of all light, but the edge portion, what will have? The violet will be
Diminishing.
yeah, somewhere near to that point. So if you see it on a white paper, you have a white paper. So, so I have a white paper here. This is actually the screen. I am showing it as a white paper. So from here, your interference happening, and it composed of your red. The red light is coming, and red light is making an interference pattern like this way. Okay. So what you will see here, you see if your only red light is there, you will see a band of red here. Okay. Then next position, another band of red here. This will be the pattern which you see if you are seeing it in a paper or the screen. This kind of band of red you will see. This white portion is actually dark. You will not see anything there. Okay.
But the center one will be having maximum intensity, sir.
Yes.
And the other up, there it is at the bottom and at the top. The
Yes.
fringes, what will be having, it will be lesser intensity.
No, in the case of a perfect interference, all the fringe will have the same intensity. Actually, you are seeing like lesser intensity because
Oh,
that
yeah, it is the
this is
same.
not, yeah, this is not the point.
Bending, it is the same in both.
Yes, but yeah, the
Because there
problem.
is the same wavelength.
Yes.
Okay.
The problem which we are facing is like that way. It is not according to the interference theory. It is like a point source is here. This is a point source. This is a point source. So the from the source actually, the light will go in similar manner.
Okay.
But we cannot ideally make a point source. The source will have a particular dimension, and usually actually we will split the amplitude with two what you call two small slits which have a particular dimension. So Along with the interference, there is a diffraction effect also there. So because of the diffraction effect, actually you cannot see like a perfect interference pattern. Because of the diffraction effect is coming, you will see there's a central maxima, then you can see that it is coming down, down,
Yeah.
like that way. This is the thing which you will get, and this effect will be decreased when you are decreasing the size of your slit. When your slit size is very small, you will see that this all mm, fringes will have almost the same size. When your slit size is max, when it is increasing, you can see that the center will have higher and the middle portions. This actually you can say that it's a two slit diffraction. You can say if you are getting like this way, the diffraction effect is more comparing with your interference effect.
Therefore, the fringe intensity, it depends upon the size of the aperture,
Yes,
size of the.
yeah, size of the aperture. But yeah, in the case of an interference thing, we are actually, we'll say that size of the aperture is so small such that it will not be this much thing. So actually, in an ideal case, you will get a same fringes. So in the case of a, if you are taking very small aperture slits, actually you will get a, actually what you will get, actually you will get almost the same size at the middle portions, and you can see that the intensity will diminish as you are going away from this size. So there are like a, yeah, practical cases like, yeah, the distance it has to travel more. But yeah, in an ideal case, it's like a point source, so it will emit and there is nothing to remove. Only the path difference is affecting the interference pattern. So it is not like a, if you increase the more path, actually in an ideal case the intensity should not go down, because we are not considering any scattering and other things. But there is actually air medium inside, that air will absorb or scatter some portion of the light. So it's like that way, as you are increasing the path, you will see that it is getting diminished. But in the case of an ideal case, every intensity should be same in the case of interference. So but in the case of a diffraction, actually, yeah,
Yeah.
since you are not doing any diffraction experiment, by mathematically you can see that it will be something like a sin h by something, some function will come.
Okay.
The function will have the property like a, it will have a decreasing intensity.
Okay.
That is actually because of this diffraction effect.
Okay.
Okay,
Right.
yeah. Now see, this is only red. Now I am going to say that I am going to put a violet along with the red. Just see that violet, or just see that white light is coming, it containing one side red and one side violet now. So it's like a,
Right.
everything is coming here.
Right.
What will happen when violet is reaching here? It will also produce a maxima at the center, but bending of a violet is less compared with your bending of a
Right.
red.
Right.
So the next position, red is reached till here, that's why you got a maxima at this position. But violet will not bend that much. By reaching here itself, violet will give a maximum.
Okay.
So,
Yeah.
so you will get something like this. So what you will see, along with the red, violet will be here at the middle portion, and the other violet will be some more offshooted here. Okay. So between this violet and red, all other color will be arranged.
In between. Yeah. Right.
Yeah, like that. Yellow will be somewhere here, and green will be somewhere middle, like that way. So based on the wavelength, actually you will see a distribution of color.
Okay.
Middle portion will be always have, everything will come there and get interfere. You will get a bright
Right.
white fringe at the middle.
Yeah.
But yeah, as we are moving away, you will see that different colored, like some rainbow kind of thing you will see. That's actually you are seeing. If you see, like you are seeing actually through this CD now, you try to like reflect some light from your CD to your wall. Actually, what you are seeing, the CD containing a lot of numerous lines, and from the lines, actually, this diffraction and interference thing occurs, and that's why you are seeing the. Since you are using a white color, you are seeing a some rainbow kind of thing.
Yes.
Just put a laser light having only single light, you will see that different dots will be arranged in the wall, like numerous dots you can see with the same color. But if you are using a white light, you will see different color. That's happening because of that
Yes.
the position of the interference or the diffraction is happening at a wavelength. It depends on the wavelength, and so happening at the different positions in spatial. So you, if you use a white light, because it's containing a spectrum of wavelength, you will see the colors are arranged in that manner. And like that way, you cannot interfere white light, like red light and blue light, you cannot interfere because there's a big wavelength difference between them. So only the particular wavelength will get interfered, but that will interfere at a different location. So you'll see a distribution of color. Okay. So you will see a bright fringe at the center with the colored fringes either side. Okay. Let's see. A Newton interferometer is being used to test a lens. If the lens is either a convex or a concave lens, which of the following represents the fringe pattern without tilt, obtained with the reference as a standard plot? This is actually, I think, it's already discussed in the class now.
I understood it was only a concentric circles, but the difference in diameters.
Yeah, it will be concentric circle when
Yeah.
the fringe will be concentric circle. Now you can see that. Hmm, now we see how in the case of a Newton's interferometer, this hmm, what you say, interference fringes are obtained. Now you can see that there will be a flat.
Yes.
Okay.
At the top of it, there is a convex.
Yeah.
Or a concave.
Or convex or concave. Before that one, actually, I am moving to a concept of air wedge.
Right.
Okay. So, you people know the air wedge experiment?
I am totally I am the new person for this branch.
Okay, okay. No, no, don't worry. So, like a so air wedge experiments means you will have a slide. Like whatever you understood about this Newton's interferometer, na? So, there will be a flat, that kind of you will have a slide.
Okay, fine.
You know a glass slide, na? Normal glass slide. It's a piece of glass, that one. It will be look like this way. Microscope slide you see, it will be something like this. It's a piece of glass only. Understood?
Yeah.
Now, so it will be like this way. It's a plate, glass plate. You can understand. Okay, it's a glass plate. Now keep one more glass plate above this one. Second glass plate. You keep above this one.
Yeah. Yeah.
Okay, it will be something like this. Okay, and I am checking it through this way, one side. So this is my glass plate 1. Second one is my glass plate 2.
see.
Okay, it's
Yeah.
clear, na?
Right.
Yeah. Now I will illuminate this portion with a light.
Right.
I will use some sodium vapor lamp or something, and I will illuminate this portion with a light. What will happen if you kept the two glass plate together? What will happen? There will be a slight air gap in between this portion.
Yeah.
Okay.
Right.
Yeah. What happen when a light is coming? Light will come. Light will reflect from this side. Okay. Top side. There will be some reflection, and something will go transmitted here. Okay.
Right.
I am not at all considering about this top reflection. Okay. And after transmitting, what will happen? There is a glass air interface here.
Right. There is one, and the one another.
Yeah, another one also there. It's a air glass interface is the next set. So here will be some reflection, and something will transmit here. Here will be some more reflection, and that will
Right.
transmit through this one and come here.
Right.
Why I am not considering this reflection from this top surface and this bottom surface? Because there is a big gap that is like a much higher comparing with your wavelength of your light.
Mm.
So most probably I will not get any interference with the respect to this path difference.
Mm.
So, but here is a very thin gap. Okay, here is a very thin gap. So there is a reflection from this glass air interface and this air glass interface. So there will be some small path difference,
Path difference.
and this, you can say this is actually your amplitude splitting. Here there's a amplitude is got splitted, and there's a this traveled some extra path, then again some amplitude got splitted. Okay,
Right.
so it can interfere, and this what is the path difference? This is the path difference. If you see that
Yeah.
air gap some more bigger, I can say that what is the path difference? The
Then this one will be the
light came,
thickness of the air gap.
yeah, not thickness of your air gap, it's a double the thickness of your air gap. From here something got reflected, then just came back, then reflected here. So if the thickness of the air gap is t, then again one more t, small, 2t will be your path difference, where t is the thickness of your air gap. Okay, understood?
Right.
Yeah.
That becomes
Yeah, if this 2t, now you see that this air gap is a constant. So it's like you kept it two slides exactly same. One slide upon another slide, if you kept it, almost the thickness in between will be constant. Okay,
right.
yeah. In that case, this thickness of this air gap will be constant.
Yes.
So what you will see, if 2t is actually matching with your lambda, you will get a constructive interference.
Yes.
If 2t is matching with your lambda by 2, you will get a destructive interference.
Okay.
What you will see, if it is constructive interference, you will see, if you look from the top side, you will see it is like a full bright only. If it is a destructive interference, you look from the top, you will see complete dark only. So there is no fringe at this position. If it is a construct, and whether you can ensure that whether that gap will be exact lambda or lambda by 2, you cannot. Na. In the practical case, if you kept the two slides together, you cannot even ensure that it is exactly lambda. Sometimes that gap between them may be some 3 lambda by 2. It will either give full constructive interference or it will not give a destructive interference. So that you cannot ensure. Correct? So what we will do? We will keep first slide like this way. Okay. But in between the second slide, I think some people will be familiar with that experiment. What we will put in between? Tell the people who know. At the one,
Maybe paper.
yeah, paper it is there in your question. Nobody did this experiment.
First year I did this.
That time you put a paper.
Paper or anything, any sort of.
One common thing which you used. I use one common thing. You used the paper only in between that slide.
That's what I remember, sir.
Okay. Who else is there?
Oh,
I just want to see who used that. Somebody used some other thing. Kiran Jot, did this experiment? Air badge experiment?
No, sir.
Okay, you didn't do. Okay. We used a hair actually.
sir.
Okay.
Okay.
So we want something which is a very thin, but it will give a small gap from one edge to another edge. You understand, Raju sir?
Okay, right, sir.
So it will form a air wedge. That is we called air wedge experiment. One portion will be touching each other. Another end of the slide, it will be like there will be a slight projection, slight upside, and that gap is so small. It's like it will be sometimes it is a hair. So your slide will be look like one slide, and then there will be one hair. We will keep it like this way, and above that one we will keep another slide. Got it?
Okay, sir.
So that side where you kept the hair or that small piece of paper will be a little bit projected. It will be a little bit up. So what happened here? You can see that there is a continuous path difference from one side to another side.
Right.
So what will happen? Now, if you illuminated from here, using a lamp, sodium lamp or something, what will happen? I am not at all considering about the reflection from this top surface as well as this bottom surface. So I am considering only the required reflection from here as well as here. Okay.
Right.
So similar thing. If 2t is equal
It's a
to
lambda.
some n lambda, it will be constructive interference. 2t is equal to some
N plus.
yeah some yeah it will like you can say that 2n lambda yeah some
N plus 1.
2n plus 1 lambda by 2 it will be
Right.
destructive interference. But now you see that it is like a t is changing from one side to another side. So it is sure that at a particular t there will be some constructive interference will happen. Okay, you understood?
Right.
If you get, just think that here you get a constructive interference at this position.
Next question.
At this position you get a constructive interference. Okay, at this position I am saying you get a constructive interference. Okay. Okay.
Right.
Now you see here actually my light traveled this much distance. So here actually what happens, 2t or 2t1, I will say the thickness here is a t1. 2t1 was some
10 lambda.
Lambda. Then at what position I will get the next fringe? After some time, I will get a fringe.
2t2.
Yeah, let it be 2t2. What will be the next one? Next fringe will be come from n plus 1 lambda. It's true.
Correct.
You understand clearly?
Right, sir. That is the
Yeah.
next one more
Yeah.
fringe it comes.
Yeah, one more fringe will come corresponding to some extra path difference of some lambda.
Right. 1 lambda it's added.
Yeah, 1 lambda is added at this position.
Right.
Actually, there's a 2, this 2t2. So it's like some lambda by 2 got added at this position.
Okay.
Okay. So what you will see here, if you look from top in this apparatus, you will see there will be two arrangement with the two slides, and you can see that actually there will be bright fringe, then in between dark, then in between bright, in between dark, in between bright, in between dark, like that you will see. And you can see it is like a next at after some time, what you will say 2t3 somewhere here, you will see n plus 2 lambda. When it is getting satisfied, you will get one more fringe there. Okay, you understood?
Right.
Got it? So you can see that it's like a linear relationship. So
Okay.
what is getting added? The thickness is getting increased, 1 lambda is getting added. Again thickness is getting increased, lambda is getting added. So you will see that in this case actually the fringe will be almost like a equally spaced. Understood?
Right.
Understood clearly?
Right.
Yeah. Now you see what is the shape of this structure? It is a linear wedge. Wedge means this is a gap, like a, you know, the wedge means it's a linear kind of thing. Now you see this, if you did like this way, you will get a equally spaced interference pattern.
Okay.
But now go to your two lens. How it will be arranged? There will be one, your
Make it, sir.
our flat, optical flat will be there, and above that one you are going to keep your lens. Okay. So if you look at from top, you will see some optical flat, and above that one your lens will be there. Something like this way you will see. Okay. And similar thing, the experiment is similar. You will illuminate with some light from top. What will happen? You don't need to consider about the reflection from this top and this bottom. Only you have to consider about the reflection from this side as well as this side, or this side as well as this side. Similar thing here. When your 2t1 is equal to n lambda, you will get a bright spot. Next time 2t2, that will be t1, 2t2 become n plus 1 lambda, you will get a next bright spot. 2t3 became n plus 2 lambda, you will get a next bright spot. Okay,
Right.
clear? Now you see the shape. It is a curved thing. Okay, so
Right.
the distance will increase much more faster than a linear thing. Okay, got it?
Right.
You are moving from center to one side. Your the air gap will increase much more faster or much more steeper, you can say, while moving from one point to other radius. Okay,
Right.
so the path length which will come as a n plus 1 lambda will come much sooner than from center to first one.
Yeah.
Got it?
Yeah. Yeah. Now I understood. Yeah.
Yeah. So how will be the fringe pattern? The middle portion will be somewhere near. Then it has to take some n plus 1 lambda. Then it will be something like this way. Okay. This is let it be n lambda. This is n plus 1 lambda.
Understood.
But when it is coming to n plus 2 lambda, already there is a gap is much more.
Right.
So it don't have to go that much distance which we traveled here to reach n plus 2 lambda. So it will come some more closer. By this close from if you are moving from this to this, by moving a little bit here, already it has a path length some more higher. So it will reach this n plus 2 lambda sooner. So this distance will decrease. Then we are going to the next n plus 3 lambda. Actually, it don't have to go much more that much. You have to go some more here.
Right. Right.
Yeah. Now you can see that this is not a
It's not a
slide kind
linear
of
path.
thing.
It is. Yeah.
Yeah. So it is like a fully curved path. So it has a circular symmetry. So you will get something like this way.
Circular unsymmetry. It is.
Circular symmetry, you can say.
Circular symmetry, but the width it will be different.
Yeah. Width is different. You will get a concentric circle. I'm saying that.
Constant circle. Yes.
Yeah.
Concentric circles with the difference in the width of the fringes.
Yes.
Right.
Even though, yeah, width of the fringes almost look like same.
The difference in
Yeah, but the it is actually,
closeness. It is.
yeah, actually you cannot actually, if you are seeing this one, you cannot actually see how that width of, yeah, there will be some small difference, but actually you cannot exactly see the width, but you can actually see that it is coming much more closer.
Okay.
Okay, so if you are using a lens, because of this curved nature, you are getting a concentric circles. Why you are getting a concentric circle? Because your lens have a circular symmetry. So instead of fringe, you will get a circular fringes. Because the lens curvature is determining your path length, you will get a this concentric circle will coming close together.
Closer.
Okay. So yeah, now you see that which can produce a fringe like a form. Just
No, this will not. This will be having only
for
suppose if it is a cone,
yes,
then it may be right.
yeah. If it's a cone, it will produce something like this way. Got? Because it is like a exactly like our air wedge, but you use a circular symmetric air wedge.
Yes.
So yeah. So it's like if you use something like this way, one optical flat. So if you use an optical flat and something which is have a circular symmetry, but it is something like this way. So it will look like a round only, but yeah, will be something like this. Say, will be a cone. Okay, this will produce a fringe of a
Concentric circle.
concentric circle with the equal spacing.
Equal space.
Okay,
Right.
what will produce this kind of thing? You can see that it does not have an equal spacing.
That is sort of flat.
Yeah, but you can see that from left to right, it is actually the spacing is decreasing.
Right.
The spacing is decreasing means it is have a curvature at that side,
Okay.
but it is like a line. Now tell what kind of thing it is will produce like an option B. What kind of thing will produce an option B? If it's a equal spacing, it will be a flat kind of thing, or flat with having a linear curvature. Now I cannot say, yeah, it has a linear wedge kind of thing. But it, you can see that at the two sides actually it is showing the fringes are coming together. That means it has a circular curvature kind of thing. And it has a circular curvature thing only in one direction, not in another direction.
Right.
So what will be that one? It will be a half cylinder. So if you look like from one side, it will be look like a one lens only. But if you look from top, you will see that it will be like something like this. Okay. So at this portion, you will see fringe as it is moving away from this one. You will see the fringe will come together. Okay.
Right.
What? Laser beam is split into two beams of intensities I1 and I2. The meshed modulation depth is obtained. That, yeah, that's a direct question.
Yeah. Is right.
Yeah. What's the modulation depth? You already know that modulation depth equation is
Models. Yeah. Yeah.
2
2I1.
I1 I2 divided by I1 plus I2.
Right.
And yeah, it can have a maximum value of what is the maximum value of modulation depth value?
1.
1. When it will be become 1?
I1
When
is equal to
I1 is equal to I2. That time you can have a very good spatial resolution in case of interference pattern. Okay, that is clear now.
Right.
Okay. It's actually, yeah, it's supposed to come one question before. Yeah, the interference of two beams can be described by this equation. I is equal to I naught into 1 plus gamma cos delta. The I naught, gamma, and delta of the equations are, how we are getting that equation? Actually, that equation we can rewrite it as I is equal to I sorry I1 plus
Plus I2.
I2 plus square root of
2 root of
I1 I2
divided by.
cos delta. You can
Yeah.
write.
That's right. Right.
Yeah.
Right.
Take this I1 plus I2 outside, then you can write as I1 plus I2 into
1 plus.
1 plus 2 square root of I1 I2 divided by I1 plus I2 cos delta. This is actually changed to I0 plus 1 plus gamma cos delta. Now from this one actually it is clear. I0 is your it's the total intensity of these two beams I1 and I2, and gamma is the modulation depth, which is given as 2 into I1 I2 divided by I1 plus I2, and this delta is actually the phase difference between these two beams, which is producing this intensity I1 and I2. Okay, so yeah, that's a direct question. So this is the bias intensity, which is actually that depends on the intensity of the individual beams. Then second one is the modulation depth, and the third one is the phase difference between the two beams. Okay, any doubt for that one? Clear, na?
Right.
Okay. Next, now it's the same thing. So you have the equation, you have the apparatus, and you are going to experimentally measure something with this equipment. So a phase stepping technique is used to obtain the unknown delta in the equation from the previous question. What is that phase stepping technique? The same thing which we told in the first thing, the microsine interferometer. You can shift your mirror such that you can see that your fringe will move one side. You can see that okay, the fringe one fringe move or the another fringe move. One fringe is moved means actually you made a phase difference of 2 pi. One full fringe moved means one fringe pair. One dark and bright band moved means you made a phase shift of 2 pi or a path length of lambda. This is the thing. Like that way you want to move. Why? While moving actually you are the one who is moving. So you know how much distance you are moving. And you can see how much fringe is getting moved. So these are the things you are going to measure. Okay. So this thing, the same phase stepping technique is used to obtain the unknown delta in the equation from the previous questions. The minimum number of phase steps required to obtain delta is. Now actually we know that actually there are three unknowns in the equation. What are the three unknowns? Because you are going to measure I. I is a, you can say it's like a, this is the dependent variable. But you have three independent variables. You have I naught, that also you don't know. Because you are only getting the sum and gamma or your modulation depth, that also you don't know. And the delta, the phase difference between the two beams, that also you don't know. So you only get based on your movement, you will get some different intensity. So in order to get that difference in intensity, actually you know that there are three variables. To solve that three variables, at least you have to perform your experiments in three different ways. So the minimum number of phase steps required to obtain delta is actually 3.
So 3 equations are required to solve it.
Solve that equation. Yeah, solve that variance. Okay. Actually, this directly depends on the phase. While moving itself, actually you are moving the phase. So at least if you can keep at least one quantity same, you can calculate. But while moving each time, actually you are going to change your phase.
20 equations you are right.
Yes. Now, yeah, 8th question. This is the question which I explained, not the question, the thing which I explained before. to say the Newton's ring experiment. A wedge-shaped air film is made between two sheets of glass with a piece of paper of 66.18 micrometer thick, used as a spacer at one end. The light wave is 500 nanometer is incident from directly above. Determine the number of bright fringes that will be seen across the wedge. This is the question. So this is the same experiment which I explained that time. You will have a two glass sheet. In between the glass sheet, what you kept? Yeah. During my college experiment, we kept a hair, and that's thickness that you can see. It's a 66 point some 18 micrometer. You can see that it's a normal hair will have almost like a 50 micrometer size. So that's why we are using hair as a very good thing for this experiment. We just keep one hair strand in between the glass slide, and we tie to these two glass slides together using some rubber band or something such that it will form a nice wedge. Now the question is that, yeah, you used a 66 point
8 micrometer.
so so an air wedge is made using a glass sheet at one side, sorry, paper sheet at one side having a 66.18 micrometer. You want to see how many fringe will be seen in between. Okay, so at one end you see that it's like there is no thickness at one end. Okay, this actually two glass slides are actually touching each other, so there is no gap. Okay, true. When you started seeing a one fringe, when this gap became
Small.
2t1, let it be first one, 2t1 will become
Lambda.
lambda. Okay, then or t1 is equal to lambda by 2. Next time when you will see that one, 2t2 will become 2 lambda, or t2 is become 2 lambda by 2. Okay, so they are asking how many fringes you will be seeing from here to here. So lambda corresponding to your first fringe, 2 lambda corresponding to your second fringe, 3 lambda corresponding to your third fringe, and here the thickness is like lambda by 2. This is 2 lambda by 2. This is 3 lambda by 2. This is thickness. And what is the last thickness? Last thickness is your paper thickness.
Yeah.
Let it
10
be,
lambda by 2.
yeah, let it be m fringes you are seeing. Then the corresponding thickness will be m lambda by 2, and that thickness is actually your paper thickness, 66.18 micrometer. Okay, so you know the lambda, you want to know only m, so m will be equal to 66.18 into 2 by lambda. So can say 66.18 into 2 by lambda will be 66.18. It's a micrometer. You can raise it to minus 6 into 2 divided by lambda is 500 nanometer. So you will get some 264.7. So you see that a full band of some 264 fringes you will see complete. You don't, yeah, if you are counting like that way, you may see some 264 full fringes. Okay.
Right, sir.
So the next question. A thin film of refractive index NF and thickness of D is coated on a glass of refractive index NG. The surrounding medium is has an index of N less than NF less than NG. The condition for complete cancellation of reflected beam, assuming light is not multiply reflected. This is actually, yeah, this is something you have to know, but yeah, to make this, the calculation is actually, or the derivation is actually some more involved thing. So I'm directly telling this one.
So,
Yeah.
these last two questions, like they were discussed in the next week. It
Okay.
was not actually discussed in the week 10.
Okay. In that one they are discussing. Okay.
Yes, sir. Like, possible, can you like look, sir? Like, was it meant to be for week 11 or
Okay. Okay.
because it was not even discussed about the thin film? This thing it was discussed in
Okay.
the
They are
next week.
discussing the thin film there. Okay.
Thin film was discussed in week 11, sir, not week 10.
Okay. Okay. But anyway, you may have go through that one, so it's not a.
Yes, sir, but we lost marks there, sir.
Okay, but yeah, I actually, but I am discussing the question even after that solution is out.
Yes, sir.
But when I am discussing the solution, this is the week actually you people may have already gone through.
Yes, sir.
Okay, that time only
But
you are
during that
understanding.
time, we
Okay,
didn't know thin films. Yes, sir.
okay. So I will directly give some equation. Yeah, it's discussing in that time. Then yeah, you will understand more. If you are quoting with a your N1 and there's a coating of N2 and then there's a coating of N3, and if N1 is less than N2 is less than N3 for anti-reflection coating, like you people may have see, yeah, I think if it's a discussion you people have know much more related this anti-reflection coating. You may see that your cooling glass have some nice color, some reddish violet kind of thing color you will see in your cooling glass. If it's a costlier one which have a nice effect or nice cooling glass, or most of the expensive, I think now it's like ordinary glass also coming with the anti-reflection coating. You can see some color like which you are seeing above, like a soap bubble kind of thing you are seeing above this glass, correct?
Some color.
Yeah, some color you can see above your specs, not only on cooling glass, some specs also you can see some color. That is actually called anti-reflection coating. So in order to avoid light reflecting from your glass, actually they are coating with some material in nanoscale range such that it will avoid the loss of light by reflection. Okay, and what you can do is like that way they will arrange in such a way that they will use the technique of interference. You see, there is actually light is coming from, light is reflecting from the top layer as well as this bottom layer, such that if these two lights are getting interfered, destructively. If two lights are interfered destructively, you will see the reflection will be minimum and the transmission will be maximum. Okay, so in that one, actually you can go for this condition for the condition for what should be the thickness. Now you say what should be the thickness for this one, that you don't have to worry much. You can easily calculate the thickness of the coating. Now that light is reflected from top layer, light is reflected from bottom layer, I say it has a thickness of T. So what will be the path difference from top the light reflected from top layer to the light reflected from the bottom layer? What extra path this light traveled to the from top to bottom again to top? How much path light traveled? 2T physically, but this layer will have a particular refractive index. Okay,
Yeah.
so
Therefore,
the layer will have a particular refractive index of
multiply by N2.
N2.
That will be the path.
Yeah. So if that path, it should be how much? The minimum path should be how much?
Should be
If it is lambda, what will happen? If it's a lambda, it's a constructive interference. You will see very good, very bright light
right.
at that position. That means if you are using your specs, you will see your specs will be illuminating. Actually, you don't want this one. Why? Because if your light is reflecting a lot of light, means the light which is entering to inside your specs is minimum. So you will not get the proper light inside your specs. You don't want the specs should shine. You want light should come maximum inside and minimum outside. So it should be lambda by 2, such that the reflecting position will be minimum. So it should be a destructive interference. That's why you call anti-reflection coating. So you don't want any glare from your specs or any reflection from your specs. The reflection from your specs should be minimum, and we are ensuring by putting one extra coating of a material here. Now you see, so 2T into N2 should be lambda by 2. So if you know the material, you can calculate T will be like a lambda by 2 into N2. Sorry, already 2 is the lambda by
4.
4 into N2. Okay, this is the criteria for thickness. Yeah, actually there are like using our wave optics, actually we can find out how much light is getting reflected and how much light is getting transmitted. Using that one, actually we can calculate what should be the optimized refractive index for N2, such that your base material is N3 and the outer material is N1, and it will following this criteria. N1 is less than N2 is less than N3. Then this is the one. I hopefully, yeah, it will be discussing in that this week's class, or you take it as like N2 should be square root of N1 and N3. So this is the criteria. These are like two criteria. This is the thickness should be like a lambda by 4 N2, and your refractive index criteria will be N2 is like a square root of N1 and N3. Actually, yeah. This actually you can directly understand from your interference experience. This is the thing which you want to know. Yeah. So yeah. So the ninth question will be something like that way. So you have to understand that one. So the solution is NF is equal to square root of N into Ng. So this is the condition for complete cancellation of reflected beam. Now 10th question is actually the one which we discussed now. A glass lens coated with a magnesium fluoride film to increase the transmission of a normally incident yellow light of wavelength 550 nanometer. So what they will use, usually they will use, because if you take a spectrum of sunlight, if you take a spectrum of sunlight, you will get something like this way. And you are like a yellow, green, that range will have a maximum amplitude. So for an anti-reflection coating, actually it is like a, it highly depends on your wavelength of the light. And you cannot say that every wavelength should be not reflected in my glass. So corresponding to each wavelength, you may have to use a different kind of thickness as well as a different kind of refractive index. That is not going to be a practical case. So what they will use, they will see the spectrum, and corresponding to the spectrum, what is the like a maximum we have to avoid. So you can see in the sun spectrum, the peak will come around like a bluish yellow region, and we will use that one as your wavelength corresponding to the anti-reflection coating. So the reflection will be minimum for that particular wavelength. That's why the middle portion of the spectrum is actually completely diminished. That's why you are seeing your this coated specks as like a mixture of like red and violet kind of thing. So the middle portion of the spectrum is completely gone because of it has the just not at all reflecting. So what you are getting reflected is like your two edge of your VIBGYO, violet as well as your red. Yeah, sorry, I lost the connection. So where I stopped when you people stopped hearing. Hello, hello. Am I still not audible?
You're audible.
Okay. Yeah. So the anti-reflection coating wavelength will have a special thing. So we used that middle portion of our solar spectrum as our usually normal wavelength for anti-reflection. So when that portion of the wavelength does not have any reflection outside, the remaining side, you can see the two edges, like this your violet bluish edge as well as your reddish edge will have a combined effect, and that you will see it as your color of your reflection coating. So you will see something like a some brownish tint or like a violet plus red mixed kind of thing as usually your color of your specs, some tint. Understood? So the 10th question.
Yes, it's a direct question.
Yeah, that's the thing which we discussed just before. So a glass coated with the fluoride film to increase the transmission of normally incident yellow light of wavelength 550 nanometer, the minimum thickness of the magnesium fluoride. Okay, so so this is the equation which we just derived. The thickness should be minimum thickness should be lambda by 4 into refractive index of that material. So we have lambda is there given. So T is equal to 550 into 10 raised to minus 9 by 4 into what is the refractive index? 1.38. Four into 1.38. And it will come as
99.64. 637.
divided by 4. Yeah. Right. Yeah, nanometer 99.63.
99.637.
Yeah, 67 nanometer. Okay. So yeah, I was thinking that I can do some MATLAB thing also, but yeah, that discussion was very good, such that yeah, I thought that we will complete this 10 question within like a short time, but yeah, it was nice. Yeah, we discussed much today. If you want, what you want to see something extra or something, you can do.
So, is it any possible that the question 9 and 10, because that was not discussed, sir. I tried searching in week 10 lectures. That derivation concept was not even discussed. In week 11 only it was discussed.
But yeah, but question 10 I cannot do anything. Na? Question 10 is
Huh.
actually you can derive. Question 9, okay,
Huh.
I can tell to them, but I'll see
Okay.
that what they are going to tell. But yeah, they'll tell that okay, you may have to see 1 week ahead also. But yeah, that I'll
Okay.
check.
Yes.
But
Fine. No problem.
10 I am sure that they're not going to, because yeah, without
Yes, sir.
understanding the concept, you can solve that
Yes,
10.
fine, fine. So, and there was some mention of that practical labs of them showing uh, the holograms or something in week 11.
Okay, let's check.
Is there any way that we can also get access to that in week 11?
Week 11.
Like
Let's see.
practical,
Okay, that I
uh,
think that may
they
not.
said that ma'am was referring that did you guys go to the lab and check the.
Okay, that is actually, yeah, this is actually these are rerun course now. This actually, this course was actually came along with the students which we studying in campus that time.
Yes, sir. So, like, is there any like virtual research resources that we can access?
Okay, that I'll check whether they took any video or something, whether it's
Yes, sir. Yes,
available
sir.
that I can see. Sometimes that may be available. Some
Yes, sir.
because we
That's all.
saw some photographs.
Okay.
And what about this MATLAB or Python? How you could have done some simulations and other things, or you completely avoided that such that it's not a problem there in question and answer means no assignment and
Assignment was not there, so we
yeah,
didn't
that's
try it.
so. What about Kiran? You could do some simulation in your Python.
No, sir, I also didn't.
Okay, you didn't try it. Okay, okay. I can just show one screen such that it is. You're seeing my screen. This is the
Yes, sir.
code which they run. Uh, this is actually made in a 3D form. This is actually a simulation which is showing the interference pattern of two beams. Okay, this is actually this code is written in MATLAB. I am familiar with MATLAB, so I am using MATLAB only. If you are familiar with any other things, actually you can use any other things. This code is pretty simple. Yeah, if you people want to know MATLAB, actually you can understand. Or if you require, because I am actually familiar with MATLAB only. So yeah, I'm not much familiar with Python. So this is a single code which I made. You can go like it's actually two beams. One electric field which is made within a zero phase, and there's another electric field made a phase difference of some cos t, and the t I defined as pi by 6. So there's a pi by 6 phase difference between the beam path, and we are combining that beams together, and you are taking the intensity and you are plotting that intensity as a color map. It's a MATLAB code. So yeah, and we will get like this way. You can see that it's a bright fringe as well as dark fringe, bright as well as dark. Sometimes you may feel that it's like a bright fringe is more wider than dark fringe, but it's not like that way. So you can see that exact bright is only at the middle portion. In between, actually, it's a mixture of bright and dark. So the width of this bright as well as dark is same. So that's why in order to understand that one only, I put that is like a instead of a color map, I am going to put it like a surface plot. I don't know using color map, you can see it in color. Okay, now you can see that it's like exactly like a sinusoidal manner with it equal. Yes. Okay, now you can see now this is the intensity distribution. You can see in the case of a so it is like a equal width. This MATLAB is a good tool to do a lot of calculation as well as plotting as well as data analysis. And if you have a lot of data together, it will make your life simpler to do analysis of thousands or lakhs of data in a fast manner. So this is like you will get a feel like that way how it is getting and how these things will get changed like that. Okay. If you want some details regarding this one, you can tell. We can arrange some session for this kind of things. So I can tell that how to plot like basic functions or how to plot data or how to analyze some only small things. Yeah, if you want to tell how to use Python also, you can also use. Yeah, I would like to do it in a interactive manner such that it will be nice for everybody. So these are the things. So any doubt?
I think it's clear, sir.
So hopefully everything is going good. Now next week actually what are the things people has to study? Interferometry. Okay, in the interferometry. Holography. Okay, in the applications of interference, they may be discussing this year. Thing. So nice. One more week is pending now.
Yes, sir. And
2 weeks.
in week 11, we have a lot of same things, sir. What is there in week 10?
Means
Thin film.
okay,
Thin films are there, sir, full.
okay, okay. This is a full of thin films. Okay, hologram. Let's see. Let's see. Okay, okay. Yeah, some thin films are there. Good. Well, okay, refractive optics. Okay. Okay. This all interference and these things are actually going to end in week 11. Okay, nice. Anyway, this good experience. So prepare well for exam. But yeah, no need to worry much.
Sir, when can we plan this MATLAB session?
You people want that MATLAB simulation kind of thing.
Yes, sir.
Okay, but yeah, if you want, I can put a extra session also, no problem. When
Yes,
when will you prefer? Uh,
sir. On a holiday on Saturday, Sunday, if possible.
yeah, I can put this extra session is not at all a problem because yeah, so all other I have a constraint like to put a normal session only. They said that okay, I had to try to fix on that particular session. But yeah, if it's like extra session, that's I can do no problem.
Okay, sir.
So when you prefer for this one, you can tell. If I am free in that day, I can do no problem.
Sir, Sunday, if possible.
Okay,
You
Sunday.
can ask.
Okay, I'll check my thing, and if possible, I'll put a message in that on Sunday, such that we can have it. Okay. And what are the things you expected? It's like only this interference part, or or I can say that how the basic we can how to take data and how to plot along with this one. We can discuss this interference thing also.
Yes, sir.
Okay.
Yes, sir. And also, like, how can we like use it in our like, if any skills that we can use?
Yeah.
with MATLAB.
Yeah. That I'm saying. Okay. How?
Yes, and how we can use it in like any optics job if we do get it. Like,
Yes.
how,
That I'll
yes,
say. So it's like a, so MATLAB is like a, everything is actually you are doing with the matrix. So the matrix laboratory. It's like that became MATLAB. So it's like everything you are dealing with the as matrix, and it's like matrix analysis, and yeah, it has a lot of functionality and you can use like a lot of things. Even when I was using that one, I didn't even realize how much powerful is that. But when I was using like thousands of data, because I had a machine which will take data like per second. It has some sampling rate of like a 2.4 gigahertz. So it's like a, and it will have some 11 megabyte or something. Yeah, it's like it will take lots of data at a single stretch. So analyzing the data is like a, it's a very difficult task. But yeah, if you put it in the MATLAB, it will like it will make different. Yeah, you have to write the code, you have to know the logic, but yeah, if you made it in that code manner, then yeah, just like you can graphically analyze the data. That's very nice.